Hey, Mr. Adam here. We're going to do some standard heats of formation, calculating the heat change of a reaction here. If you're ever getting the delta H of a reaction, you can find the overall reaction by using standard heats of formation. Usually we can tell this by they give you a table of numbers. This is when we use this method here. Okay, the standard heat of formation of a compound is the change in enthalpy that accompanies the formation of 1 mole of substance from its individual elements in their standard state. Okay, it has to be their standard state and it has to be individual elements. Okay, the standard is used to determine the state called state, ambient temperature, and pressure called SATP. Conditions are 1 atmosphere, that's the standard pressure, and the temperature of 25 degrees Celsius, because it's ambient temperature, which means it's really room temperature. Here you notice it's different than STP. Okay, heat of formation of the elements in their natural state is 0, because they're already formed. So you know. We are going to use this reaction, this equation. Delta H of reaction equals the heat of formation of the products minus the heat of formation of the reactants. This is a summation symbol here. Summation. I think that's how you spell it. Okay, that means all the products minus all the reactants here. Okay, you have to convert these to kJs though, and you'll see what I mean here in a second. Okay, so write the standard reaction and formation for the calculation of entropy for the combustion of sucrose here. So the first thing we have to do is write the combustion of sucrose. Hopefully we know that sucrose is C12H22O11. We are going to add that to O2, and we are going to produce, because we're doing combustion reaction, CO2 and water. This is a great reaction. The balance here, 12 carbons here, so we're going to put a 12 here. 22, so we're going to put 11 here. And then we're going to put, 11 oxygens, so we're going to need 12 oxygens here, okay? So, delta H is going to be equal to products minus reactants. Okay? Remember, these are the products. Okay? So, delta H here is going to be equal to, and what I do is I use big brackets here to first do the products. So we're going to do carbon dioxide, which is negative 393.5 kJs per mole. We're trying to figure out delta H, so we need to multiply it by the number of moles, which is 11 moles, plus negative, well, that's not negative 11 moles, that's 12 moles, Mr. Aerodom, come on. Negative 242 kJs per mole for water times 11 moles. That is going to be minus our reactants. Okay, remember the reactants are over here. So this is going to be minus 2226 kJs per mole times 1 mole. And you notice that oxygen is not in the table. This is an element as natural state, so the answer for the value for that is 0. Okay. And then you just have to be careful while solving this here. Minus a minus is a plus, so this is plus 2226 kilojoules. And then negative 393.5 times 12 plus a negative 242 times 11 is negative 7834 kilojoules. And then you combine this. Remember, I already took care of this minus because it's minus minus is a plus. And I end up with negative 5158 kilojoules. This is exothermic. Delta H is negative. So if I was putting this in my reaction, I would put it right here, 5158 kilojoules, because it goes on the product side if it is exothermic. Moving on to page 12. Hey, nitroglycerin is a power explosive that forms 4 gases when detonated. Good fun there. Use the values in the table to calculate the enthalpy change when 10 grams of nitroglycerin is detonated here. Okay, so we're going to do delta H equals products minus reactants. Okay. Okay, these are the products, right? Yes, they are, Mr. Harridan. Nitrogen is an element in its natural state, so we do not need to use that. Oxygen is an element in its natural state. We do not need to use that either. So we are going to start off with delta H equals bracket bracket carbon dioxide gas, which is negative 393.5 kJs per mole. Times 12 moles plus negative 242 kJs per mole for water times 10 moles of water. Moles cancel, moles cancel, moles cancel. And that is my products. Minus my reactants here, which is the nitroglycerin, which is negative 364 kJs per mole times 4 moles. Okay, let's simplify this down here. Negative 364 times 4 is negative 1456. Now this is a negative negative again, so this is going to be positive 1456. Negative 393.5 times, oh, that's a plus sign, times 12 plus negative 242 times 10 is negative 7142. And then we combine those and we get negative 5684 kilojoules. This is exothermic, negative delta H, So we're going to put this on our product side, 5684 kJs. It says use the values to calculate the enthalpy change when 10 grams of nitroglycerin is detonated. Oh, you know what that applies? Stoichiometry, because everybody loves stoichiometry. I love the stoichiometry music. So now we're going to do some stoichiometry. This is exothermic, remember. Delta H is negative here. Remember, we're going to convert to moles. And then we're going to wham wham. So we're going to start off with 10 grams of nitroglycerin, grams on the top, moles on grams on the bottom. Well, grams on the top, grams on the bottom. What are we trying to convert to? Moles of nitro, grams of nitro. This is 1. And then molar mass of nitroglycerin, we all know it's 227.1. And then step 2 is the wham 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 wham. Moles of nitro on the bottom. Kilojoules of nitro on the top. Wham 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 wham. 4. Wham 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 wham. Negative 5684, since it is exothermic. And we get an answer of negative 62.6 kilojoules. Easily done. Hey, the first step in producing nitric acid from ammonia involves the oxidation of NH3. Using the following values in the input, calculate the enthalpy change for this reaction. Is the reaction endothermic or exothermic? Okay. Delta H is equal to products minus reactants. These are the products. So delta H is equal to 90 kilojoules per mole times 4 moles plus negative 286 kJs per mole times 6 moles for water. Close our brackets, our moles cancel, minus brackets for the reactants. We're not going to use oxygen because that is an element in its natural state and the value is 0. So this would be negative 46 kJs per mole times 4 moles. And then we're going to solve. Okay, 46 times 4 is 184. Negative, negative, that becomes a positive. Positive 184. 90 times 4 minus 286 times 6 is negative 1356. You add those together, you get negative, and you can't see any of the adding I'm doing because I'm not on the screen. Awesome. 1172 kilojoules, which means that this is delta H is negative, exothermic, heat goes on the product side, 1172 kilojoules. Okay, you guys are champions. Legend is